Welcome to the first session in this mini course in CUDA. I'll be starting from the very beginning, the basics of the GPU and CUDA language, and I'll be showing some examples of running kernels and debugging different errors in CUDA. Also, if anyone has any question in the middle, then just ask the question. So we start by presenting the top level structure of the GPU. Every GPU is composed of streaming multiprocessors, and it depends on the specific GPU. Some have, like the 3090 has 84 streaming multiprocessors, 4080 has more. And these are the basic units. Then each streaming multiprocessor has some CUDA cores, usually 4 or 8, where each core has a scheduler that can schedule different warps. So each scheduler has a few warps available, and each clock it can schedule a different warp, where each warp consists of usually 32 threads.
Hadar, I think we are still seeing the first slide, the title slide. Are you on the second slide by any chance?
Yes, I am on the second slide.
Okay.
Can't you see the...
Okay, now we can see the second slide.
Okay. Strange, but okay, thanks for notifying me. Yes, so I think I'll say every time I switch slides. So yeah, so this is the general hardware structure, and it's important to distinguish between the hardware and the software, because also in the software we speak about threads and blocks, but they are going to be translated into actual threads and warps in the hardware. So we need to distinguish between these two. Also, an important feature that we need to be aware of is the different types of memory. By the way, I switched the slide. Can you see it?
Yes.
Yeah.
Great. So we have different types of memory. If this is the GPU, then we have the global memory. And yeah, so first of all, the memory of the GPU is separate from the CPU. It's on its own device, and it has a global memory that can be accessed by all the threads and all the multiprocessors. Then there's the shared memory that is specific to the SM, to the streaming multiprocessor. And there's also the register space, the register memory that is also the multiprocessor. The register space is the fastest memory, then the shared memory, and the global is the slowest memory. So that's the main types of memory that we have. Now, getting into the actual the software, the actual CUDA language. So we distinguish between the host and the device. The CPU is called the host, and the GPU is called the device. In the language, it's basically an extension to C++, and it has many built-in functions that usually or maybe always start with the CUDA. So I'll show you some examples. Also, we have the device, host, and global to mention if it's a function that will run on the host, on the device, or globally on the device. So I have some examples. If we go here to the Icicle library, then you can see, for example, we have, for example, this built-in function, CUDA memcopy, and it transfers data between the global memory of the device and the memory of the CPU. So it receives a parameter, CUDA memcopy device to host. So this tells it to copy memory from the device to the host, and it can be also the other way. So this is a type of a built-in function. We have CUDA memcopy, we have CUDA event record, a lot of functions that start with CUDA. Also, we can see functions like this that have this device before the definition of the function. This means that this function can be called only from device code, from GPU code, and not from host code, from CPU code. If you try to call it from CPU code, you will get an error. And vice versa for the one starting with host. So this function can be used only by the host, by the CPU. And lastly, we have global. And this, you will always see this before functions that we call kernels. These are functions that run on the entire GPU with multiple threads. The device function will be a function that only a single thread uses. But global represents a kernel call, a kernel function that uses all the threads of the GPU. Okay. Now let's see what is a kernel call. This is the main important part of CUDA. A kernel is a function, as I said, that uses the entire GPU, and we call it like this. We have the function name at the beginning, and it has some special parameters: the number of blocks, the number of threads, the shared memory size, if it's dynamic, and I'll explain this later, and the stream. Shared memory and stream I will explain later, but so what does it mean, blocks and threads? So these are software concepts that will be translated to the hardware. You can define a block of a certain amount of threads, let's say 128 threads, and then you can launch as many blocks as you like. There's a limitation to the amount of threads in a single block, but there's no limitation to the amount of blocks. Why is that? Because CUDA assures you that all the threads in a single block will run in parallel. That way you can synchronize between those threads. But threads of different blocks won't necessarily be run in parallel, only if we have enough room for that, but it's not guaranteed. So that's why there's a limitation to the amount of threads that you can launch. Inside the kernel itself, you can access the thread index and the block index by using special variables. So that's about how the kernel works, and I will show an example shortly. Also, we have special functions, for example, the CUB library. These are all kinds of optimized implementations of, for example, sorting and matrix multiplication. We can see an example of these functions in the MSM code from Icicle. So, for example, the MSM uses this these sorting functions from the CUB library. So these functions it actually wraps some kernels inside. So it's a multi-threaded function, but you can use this just as a regular function, and all the parallelism is hidden from the user. So these are the main kinds of thing you will encounter in the CUDA language. Let's go back now. So let's see an example for a kernel. This is a very simple kernel, and what this kernel does is just adds two vectors. So what we can see is it receives a pointer to an array A and a pointer to B and to C, and it adds the elements of A and B to C.
Hadar,
And it so
change the slide.
yeah. Can
Okay.
you see the slide with the kernel
Yes.
example?
Yes.
Great. So, and n is the length of the vectors that we're adding. So what we can see that inside the kernel code, instead of in CPU code, you would expect a loop that runs over all the elements of the vectors of the yes. But here, it's just a single addition that you see, and the index is according to these special variables: the block index, the block dimension, and the thread index. So what this says to the GPU is for every thread should calculate its own index and then access the relevant element from the array. So for example, the first element is from block 0 and its index is 0. So IDX will be 0 and we'll add the 0 elements. And then if we go to block 1, and let's say the block is 256 threads, then we will have 256 plus 0. It will take care of the 256 element. So this is the kernel itself, and this is the example of how we launch the kernel. So we define the number of threads, in this case 256. Also, the number of threads is important for it to be a multiple of 32 because of the 32 units that we know from the size of the world. So we decide on 256. In this case, it doesn't matter much if it's 128, 256, or something else. But then you need to calculate the number of blocks that you need, because you have a vector of length n. So how do you calculate the number of blocks? Usually you use this convenient equation to take the division and then round it up. Yeah, so this is instead of using like a ceiling function. And then you launch the kernel with these parameters, the number of threads per block and the number of blocks that you need. And you give the pointers to the other parameters. So are there any questions on this example?
So the IDX runs inside the number of threads in a single block.
So the IDX, this int IDX, will be will take a different value for each thread that runs the kernel. In each thread, each block has 256 threads, and we have multiple blocks.
Know which thread is in which block?
So you should look at it as if you are a thread and you have an index. So I know if I'm a certain thread, I know I'm thread 2 of block 0. So when I read the code, I know that for me, the index would be 2. Another thread, when it runs this code, will know that its thread number is 3. So for that thread, the index, it will know that this variable will take number 3. So this variable is different per thread. That's why this variable is also in the register memory. Okay, thanks for the question. So moving on to the next slide. Shared memory. So,
do you want to mention something about the synced nature of that's why everything, like all the threads need to do the same thing?
that's not relevant at this point. Okay, so let's see now which variables go to which area in the memory. We talked about global memory, shared memory, and register memory. So this variable, the thread ID, as I said right now, it goes to the register space, and it's thread specific. For each thread, it will take a different value. Over here, we have an array of shared memory. This is an array that will be shared by all the threads in the block. So if we had 256 threads, then all of them will have access to this array. And these pointers are pointers to global memory, and these will be shared by all the blocks and all the threads. Shared memory is characterized by this underscore shared. That's how the compiler knows that it will be shared memory. And shared memory can be allocated, pre-allocated, or dynamically allocated. The dynamic allocation uses this word extern. So that's, yes, so you see that in this kernel, we use the extern. And we need to pass in the kernel parameters. The third parameter is the size of the shared memory. Yeah, we can see here below. So that's regarding the syntax of shared memory. Any questions about this? Great. So moving on, this is an entire example of running a simple kernel with the test code. So here we have the kernel from before, the vector add. And in the main, we will have the we define the length of the vector and then the size. It's a vector of floats in this example. Then we allocate memory on the host and initialize the vectors on the host memory. And then, because
if you assign something as float and something as int, they are completely different. They don't talk to one another, and they can be run at the same time.
float just has a different size in memory compared to int. And these are different type of variables.
Yeah, like I don't know, I just like when you start, like you said that the different types of processors, like one specific for float, one specific for int. So if I want to run this add function with float and int, can I do at the same time in different blocks running this float addition here and the int addition here because they don't talk to one another?
Yeah, you probably can, but not with this specific kernel.
No, just asking like
Yes. So we allocate memory on the host, and then we initialize the vectors on the host, and then allocate memory on the device, and then we need to copy the data from the host to the device because we want to run the kernel on the data, so it needs to be on the device. Then here we see the kernel launch over here. And then we copy the results back to the host and verify against the reference. And then at the end, we need to free the memory of the device and the host. So this is a general code, how a general code will look like.
Question also, like if I don't free, what happens? It stays there.
If you don't free, yeah, it can stay there and then take up more and more memory. So it's not a good practice not to free the memory.
Do we usually separate the code of the CUDA, that runs on the GPU and the code that runs on the bus using different files?
Yeah. Actually, usually you have a different file, but you don't necessarily need.
But this is the syntax that it's Ingonyama.
Yes. In my example, I'll show it. It's separated. Okay. Yes. So now let's dive in to the interesting part, to the actual resource allocation. So when we're writing a kernel, we want it to utilize the entire GPU. So we want maximum threads to be able to to run in parallel. So what limits the amount of threads or blocks that can be run in parallel? We have 3 different occupancy limiters. Either it's the amount of threads per block, or the amount of register memory that the kernel, each thread requires, or it is the amount of shared memory that the block requires. And this also varies depending on the GPU that you have. So first of all, in order to know what are the compute capabilities or the GPU parameters, you can either look here at the compute capability. Each GPU has its own compute capability, and according to that, we can see the different parameters. For example, the maximum number of threads per block is 1024 for almost every compute capability. The maximum amount of shared memory, the maximum amount of blocks per SM, the number of SMs, it's all written here. But a different way you can discover your GPU parameters is by querying directly using the code. So I'll show you how you can do that. Here is a function for querying the GPU properties. We have a built-in CUDA function, which is called CUDA get device properties. And then we can just print all the device properties that we want. So for example, so I run this function, and we can see I'm running now on the RTX 3090 machine. The compute capability is 8.6. A number of multiprocessors is 84. We see that the number of threads per block is 1024. And the maximum number of threads per multiprocessor is 1536. So this is the actual hardware limitation. And let's see why this is important. So this means that if you launch blocks of size 1024, actually you can fit only 1 block on each SM. But if you launch size of, let's say, 256, then you can make use of all the threads, the maximum number of threads. So let's see an example for this. I have here this kernel that I wrote. which is pretty similar to the kernel I showed before. It just add elements of 2 vectors. So we have the thread ID, and then x plus y is the result. And now I have a large vector, n is 2 to the 20, which I initialize. And then I copy again the data to the device. And now what I want to do is to run this kernel. So I use 256 threads per block. And now, in order how I'm actually running this, I use a makefile that either builds or runs. So in order to build, you use the nvcc command. This is the output file. This is the version of the compiler, the architecture, and libraries to include. So if we build the test, then I can now use a tool of NVIDIA that is called the Insight Systems. And the command for this is insys profile. So I can profile my binary compiled file, which is called work test. And then I get a report. This report, I'm running on a remote machine that has a GPU. I can download it to my own computer. And then I can open it in this program, Insight Systems. Okay, so what do we see here? We see here the CPU part and the CUDA part. This is less interesting. It's mainly composed of all the calls from the yes, it's composed of all the calls to the GPU. If we zoom here, then we can see the GPU part. Which is composed of a kernel and memory copies. You see that here the memory copy takes most of the time. Yeah, so this is a memory copy from host to device. It's a bit small, but it's written it's host to device. And this is the device to host. And this is the actual kernel. Yeah. And we can also right-click here, and then, 1 second. We can right-click here and show an events view. And here it will show all the kernels, and we can see over here the parameters of the kernel. So indeed, as we wanted, we have 256 threads per block, and we have 4,096 blocks. And if you do the calculation, it turns out to be 2 to the 20, as we wanted, this times this. And the important part I wanted to show you here is that the theoretical occupancy is 100%. So we're utilizing all the threads that we can use. But let's see what happens once we change the number of threads to 124. We can run it again. Yes, we can just go directly and show the kernel in the events. And now we see that the theoretical occupancy is only 66%. And it makes sense because of what we said earlier, that we have 1536 threads, but our block size is 124. So we have a third of the threads that can't be utilized. What's interesting to notice is that the time this kernel took is 110 microseconds. And the last kernel actually took the same time, although it has a greater occupancy. So can anyone guess why is that?
Threads are only waiting. Most of the threads are already waiting.
Yeah, exactly. Because the actual core can't give service to all the threads. It has a queue, and the scheduler decides which warp to schedule in each clock. So in this case, we have many warps that can be scheduled, so this doesn't actually affect performance. So it's an important thing to note.
How many warps run concurrently in an SM?
In an SM, so it's the amount of CUDA cores. I think it's 4 or 8, depending on the GPU.
This is a very nice example. Can you zoom out? Something more also interesting is the time it takes to copy the data to the GPU and from the GPU. And the red section actually takes from the GPU to the host only half the data, right? Because the result is half of the
Yes,
output
right.
side is only half of the input side. Even though it takes two times more, it's 4 times faster to copy data to the GPU.
Right. So we showed an example of an occupancy limiter, that is the amount of threads per block. Now let's see an example of a kernel that is limited by the number of registers. So actually, my test code, the type that I'm using is test T. This is the test type that I defined. And I can switch the actual type over here. So what I'm using now for testing is the scalar type from the fields in Icicle. But if instead of that I use the projective type, which is the points that use EC addition, and then I run the kernel, let's switch back to 256 threads. And now let's run it again. So again, we generate a report. We download the report. Report number 4. So now if we look at the kernel, we see that the theoretical occupancy is only 16%. Now, why is that? Can anyone spot the answer? So the answer is actually over here. The number of registers per thread. Each thread uses 232 registers, each of 4 bytes. That's the register size. That's because EC addition takes a lot of registers to perform. And now if we go back to the parameters, we see that the total number of registers available per multiprocessor is 65,000. And if we divide that by the amount of threads, let's check. So 2 to the 16 That's their number of registers, divided by 256 threads per block, times 232 registers. We get only a single block. So we can run only a single block per register. So it's only 256 threads per the total that we have, which is exactly 16%. So this is an example for a kernel that's limited by the number of registers. Any questions about this?
Well, in the profile, can we see the actual utilization of the calculation of the CUDA of the core itself? Meaning how many clocks it was idle, just waiting for.
So I don't think you can see this in this program in Insight Systems, but you can see it in Insight Compute, which is a different program. I won't go into that in this session, but probably in the next session. Okay, so the
difference is that this is the compilation, the other one is like analyzes the run. Right? They're like real-time things.
No, this analyzes the runtime too.
So why do we have to?
Just this is higher level because this analyzes all the kernel calls and everything that's happening, and Insight Compute is to analyze a specific kernel. And you can see that in the kernel before we had only 26 registers per thread, so it's a much higher number now that limits the occupancy. The last kernel that I have for you is this fake entity kernel. It does a kind of an entity, but not exactly. What we can see here is we allocate a shared memory and then the thread index. And then we do two butterflies, kind of butterfly operation. We do a plus and a minus. And then we do a plus and a minus for elements 2 and 3. And we write it into the shared memory in the indexes 0, 1, 2, and 3. Also, you can see the use of the thread index here, because thread 0 will write to 0, 1, 2, and 3. Then thread number 1 will write to 4, 5, 6, and 7, and so on.
Is the shared memory only in the scope of the single block, or is it?
Exactly. It's in the scope of a block. That's why we can use the thread index, which is also in the scope of a block. So what is happening here is all the threads are writing into shared memory, and then they are reading from shared memory and writing to the global memory result. And that's why we also need this sync threads. We need to synchronize all the threads at the end of the writing to the shared memory. So we won't have a thread that continues to read when the result haven't been written already by another thread. That's why we have this command of sync threads. And then again, we do another plus minus operation from the shared memory back to the global. So the amount of shared memory here that we need is actually, let's go to the launch parameters. We don't need this anymore. So, sorry, I meant this. So, we have 128 threads, and then we actually need only a fourth of the number of elements. because each thread takes care of 4 elements. And that's why we need 4 times the amount of shared memory. So there's the size of our element times the number of thread times 4. And we see that if we run our code now and make a report, so we run our code now, and for some reason it takes a lot of time. Mhm. Yeah, actually, I'm not sure why would the compilation suddenly take a lot of time. Before it was all good. Any questions in the meantime? Let's see.
Possible when someone's using your server.
Yeah, maybe somebody else. Two more things.
I don't think you can use it in time.
He is currently running code though.
Hmm.
Do you have any chance to run already logged?
Do I what?
Have this run already logged?
Did you prepare the report ahead of
Yeah.
time?
Okay.
Maybe deleted it because they're huge.
Because what?
Yeah, sometimes they're big files, so maybe you just clean up also.
I don't have it prepared. It's really strange because when I tested it before, then it ran just
You
fine.
want to maybe just do the calculation first of how much shared memory this needs and.
Yeah, so actually, this kernel tends to take out 50% occupancy. And if you do the calculation, then that is what you'll find. Okay. Decided to cooperate.
We'll see if it's 50%.
Yes. Let's look at the report. So no, actually, looks like the kernel didn't run. So in the meantime, I think maybe
What's n?
n
What did you say n today?
is 1 to 20, but it shouldn't
Okay.
shouldn't take a lot of time. anyway, let's go back to the presentation. So I can leave this as an exercise to the viewers. Okay. Let's move on to streams and synchronization. So when you just write in CUDA CPU and GPU code, they will run concurrently. So you can do a call to the GPU, and then the CPU will continue. If you want to synchronize between the host and device, you need to use this function, CUDA device synchronize. That's why. Sorry. Just testing this. Invalid argument, interesting. Oh, okay. We have a live example of a bug. The bug was, I'm still using the projective type. This is actually interesting. I'm still using the projective type, and it takes too much shared memory. So that is why over here, yes, that's EC entity. So I'll show you what I'm doing. So I'm using the CUDA device synchronize over here in order to catch the bug here in the CPU code. If I wouldn't do the device synchronize, then this line wouldn't wait for this kernel call to finish. That's why you need the CUDA device synchronize. So here is an example of how you can catch errors. So this is the thing about CUDA. It doesn't automatically display the runtime errors. So sometimes you can have an error and not know about it, like happened just now. That's why you usually use the CUDA get last error. And we can see now that we got an error of invalid argument. That was because
You mean like you can get a right result and still have an error somewhere?
you can also have that, but that's not this current example. Yeah, I'll show that example later. So the amount of shared memory, because we have 128 threads, and we passed a projective type, then it actually exceeded the amount of shared memory. But now when we change it back to be the scalar type, now it should all work fine. If we build and then test, now we have no error. And now it would compute correctly.
Can you get also the blocker where the error occurred?
No, not exactly. But I'll show methods for that later. So anyway, back to the streams. So first of all, I showed you the CUDA device synchronize. That's for synchronizing between host and device. Apart from that, we have a thing called streams, which enable running different kernels concurrently on the device on different streams. For example, in the MSM code, in the reduction phase, we have, second, yes. So I define a new stream. The default stream is called stream. Here I define a new CUDA stream, which is called stream reduction, and also a CUDA event, which is this event finish reduction. And I want to synchronize the two streams. So how does this work? One stream reaches a certain event, and the second stream checks if that event was reached by the other stream and waits until the other stream got to that event. So we create the stream and create the event. And down here, we wait. The other stream waits for the event of the second stream. And that's how streams are synchronized. This is important to note. And how will this look on the Insight? So this I had prepared in advance. So if the kernel calls are large and they take the entire GPU, they won't run concurrently. But once they get small enough, you see that in this area, they run concurrently. So that's how you can take advantage of streams.
So it's like different parallel kernels, smaller kernels that are running.
Yes, small kernels of a small amount of threads that don't use the entire resources of the GPU can be run concurrently in order to make use of the entire resources. Okay, so now we get to common sources of error. So actually, can I take an extra 10 minutes or?
Yeah.
Okay, so now I think it's a very practical and important part of debugging CUDA applications. So here are some common sources of errors. First of all, accessing GPU data from CPU data from CPU code will lead you to an error, a segmentation fault, and this is the thread overflow is a very dangerous error because this is an error that can lead to correct results some of the time. And you have no indication that there are extra threads that are doing extra work on data that they are not supposed to access. That's why I call it the silent killer. Another common sources of error are just it's very complicated to get the correct indexing. So usually the errors are concerning indexing or just having too less threads or too many threads.
I'm sorry, are you still on the slide streams and synchronization, or are you on the next slide? Oh yeah.
Great.
I see.
This is a really strange error. Yes. So this is the common sources of error. So we can see here in the vector addition, this is why we have this condition. We need to pass the number of elements, and if the thread index is larger than the number of elements, then we don't want the thread to do any operations.
So if you calculated it perfectly, you wouldn't need this condition.
Yes. But
like where would n come from?
So let's show an example of this exact problem. Let's say okay, so let's say this time we use this bugged kernel. So this bugged kernel doesn't have the condition of if the thread ID is larger than return. So we run the regular kernel and then the bugged kernel. We run them both with 256 elements per thread. And actually, in this case, there won't be a problem because n, which is 2 to 20, is divided perfectly by 256. So there will be no extra threads. But if we change n to something that is not divisible by 256, then we could have a problem. So let's see.
You can catch it on the calculation of the number of blocks, right?
No.
You calculate the number of blocks by rounding it to the nearest
Yes.
number.
Okay.
So if you want to do rounding, or check your rounding, check that you don't.
Check that you don't have a remainder.
everything.
Yes, but most of the time you want something that isn't necessarily divisible by 256.
Yeah, you can catch it on line 152, right?
No, because if I want to compute length of 300, then I would do it the same way. I will still launch 2 blocks of 256 and have the condition inside the block. So because I don't want the number of threads to be, I still want the number of threads to be divided by 32 according to the warps.
So in this case, basically, you would add more to the vector addition. You just add some random memory cells or something like that.
No, I will. Yes, I will have extra thread that do nothing exactly.
Okay.
So let's see. So now I want to run the 2 kernels, the bugged one and the correct one, and compare the results. So let's run test. And now we get a segmentation fault. Why is this? Because we try to print the device memory. This was planted in advance. So we need to use the host memory after we were copying it from device to host. Now if we run the code, then we get no errors on the kernels, and we actually get the exact same result. So you could think that there's no problem, but actually, and this is another trick that is good to know for debugging, you can use printf within a kernel. So you don't always have to copy the data from the GPU. If you are within a kernel, you can print it directly without copying. This is what I'm doing here. I'm printing the thread ID for each thread. So if we run it now, we can see the actual threads that are running. And we see that we have thread number 463, which is way above 300. And it's copying data from places that it should not.
So, wait a second. Fine, you do some calculation that you don't need to, but you're also
writing memory.
You're potentially touching memory that you
Yes.
shouldn't be touching, right?
Exactly.
Because it's all just pointers plus some offset.
Mhm. So actually this week, I became aware that there is a tool called CUDA memcheck that's supposed to check for such things. And there's also a tool called the computation sanitizer that does the same thing too. I managed to make the computation sanitizer work, but CUDA memcheck I haven't been able to make it work yet. So this is, but I'm just telling you that it exists. So if anyone did have success with it, I would like to know. And it could theoretically catch such bugs. Okay. So let's go back to the presentation. So lastly, I want to show some more debugging methods. So the first one I already showed you is using the getLastError to see if the kernel returned any error. You can also use actually the debugger. Then you will need to add this minus capital G flag when compiling and use the gdb/LLDB. And this can allow you to go and switch between all the threads in all the blocks and debug each of them separately. Why I don't use it most of the time is because the compilation takes a real long time once you have a long code with complicated kernels. For example, the MSM would take around 2 hours to compile in debug mode.
Also, debugging breakpoints inside those kernels is a bit tricky because you need to know exactly which thread you've landed on and stuff like that. Because everything is like duplicated, right?
So, no, you can choose the thread that you are debugging.
Yeah, of course. Like a
Yes.
conditional.
Yeah, so you can use printf inside the kernel and check if it's the specific thread that you want to debug with a condition. You can also temporarily copy some data to the host. You can run the same kernel with less blocks or less threads, and then you can control only that.
Can
Also,
you
you can
go
use-
to the next slide, please?
Hi,
Yeah, thanks.
thanks for that. So, yes, so I wanted to show you one last example regarding these three debugging methods. Let's see. So now I want to debug. I have this version of a bugged fake entity kernel, which has some bugs. So firstly, I will try to run it. And I'm getting, so the first bug was caught by the CUDA get last error. An illegal memory access was encountered. So that means that probably the shared memory index is accessing an incorrect index. How can we find this out? So I go to the kernel, and then I see maybe some of these indexing of the addresses are incorrect. So I can print all the addresses. That's what I will usually do. I will print them. And I can see, in this case, we have 128 threads. So the size of the shared memory is times 4, is 512. But we see accessing addresses in the 600s. So right away, I know there's a problem in these addresses. And then I find this small mistake that instead of 4 times the block dimension, it should be actually divided by 2. Because the stride should be half of the size of the shared memory. Once I fix this, now I get no error. But when I look at the actual results of the test and the reference, I see that they are not the same. So we still have another bug. So now a thing that I can do is take these two parts separately. I want to see if the part is in the second part of the half of the kernel or in the first one. So I can just go ahead and print the shared memory state after the first computation. So what I'm doing, I'm saying only the first thread will print the status of the memory. Because if I don't use this, then I'll get loads of prints from all the threads. And then I print the state of the shared memory. And then I get all kinds of numbers that I can't make sense of because I don't know if they were there before or is it just random stuff that was in the shared memory. That's why I first initialize the shared memory with zeros. And now I can see if the shared memory actually. Okay, so now I see that there are zeros over here. And that's not good, because I would expect that every thread will write to certain addresses. So now I want to further narrow this down to a single thread. And now I can see exactly where the thread is writing, thread number 0. So I just use one thread. Actually, I will just use one thread and one block. And now I see that I'm getting results in addresses 0, 1, 2, and 4. And I wanted to get the result in 3, not 4. So I can see that indeed I have a bug here in the right address. And now it's correct. But the problem is that the results are still incorrect. This is where I pull out my last trick, which is using these dummy variables. Instead of using the actual scalar, which is very long, I wrote this dummy class of scalars that go only from 1 to 10. And I can switch to this. And once I use that, I can debug with much simpler numbers and see exactly, go through the math and see where the error is. Once I do that, I will eventually discover that I have some error here in the read addresses. And when I fix that, and and go back to the correct number of threads and blocks, then it should be correct. Let's see. Yes, you can see that the test matches the reference. Okay, so that was, I showed you a debugging process that is fairly common when I'm working on the CUDA applications. Any questions about this part?
Nice.
Let's see. Where's my presentation? Okay, so also I will make my slides public. I also included here some resources. There's the compute capabilities table. Yes, a link to Tony's explanation from the GPU masterclass session. The best practices guide of NVIDIA, the programming guide of NVIDIA. This is a CUDA crash course on YouTube, which I specifically like the example of sum reduction. There's a good blog on the optimizing matrix multiplication and also on optimizing matrix transpose. These are very good examples to learn from. In the next session, I will be diving deeper into profiling tools and how to generate a optimized CUDA code with some examples. And also, if anyone has any more suggestion, then contact me and we can add that. You've all suggested that we add a home exercise for anyone. For anyone that wants to practice his CUDA skills. There's an exercise here to write a kernel that does kind of a fake entity. It takes every 16 elements and then computes a kind of entity using 2 stages of entity 4 with shared memory. But there's no need for them to whittle factors and multiplication, only addition and subtraction. yes, and that's about it. So, any last questions?
That was great, Hadar. Thanks a lot.
Thank you.
Could you share the branch or like whatever test code you have written so that we can go over the code again?
What would be? Sorry, can you ask that again?
I mean, could you share the reference code later that you were showing the
Yes,
examples?
yes. I will share my reference code. It's on a branch on Icicle called mini course.
Okay. Okay. Cool.
It's actually already in the server.
Okay. Cool.
Great. So thanks everyone for coming, and I'll see you next time.
Thanks, Hadar.
See ya. Thanks.
Right.
Thank you, Hadar.
Isso, obrigado.